In this lesson, I'm going to explain a very clever algorithm for calculating the greatest common divisor of two numbers. The greatest common divisor, or GCD, of two integers is the largest value that evenly divides them both. For example, the GCD of 24 and 30 is 6, because 6 is the largest integer that evenly divides both 24 and 30. One way to find a GCD is to find the prime factors for the two numbers and see what factors they have in common. I'll talk more about prime factorization in another lesson. Unfortunately, factoring can be very difficult for large numbers, so that approach doesn't work well with big numbers. Fortunately, the Greek mathematician Euclid wrote down a better method in around 300 BC. This algorithm is called the Euclidean algorithm, or Euclid's algorithm. It's an amazingly short algorithm that's easy to use but hard to understand. Here's the algorithm. To calculate the GCD of a and b, the algorithm enters a loop that runs as long as b isn't 0. Inside the loop, it calculates the remainder after dividing a by b. It turns out that the GCD of a and b is the same as the GCD of b and the remainder. So the code switches the values of the variables around to calculate that GCD. It sets a equal to b and b equal to the remainder. It then repeats the loop. The loop continues until b reaches 0. At that point, the GCD is stored in variable a. For an example, let's calculate the GCD of 78 and 66. 78 is 2 times 3 times 13, and 66 is 2 times 3 times 11. So the GCD should be 2 times 3, or 6. Now let's try it with Euclid's algorithm. Initially, a is 78 and b is 66. The remainder when you divide 66 into 78 is 12. In the next step, a becomes b and b becomes the remainder. Now a is 66 and b is 12. The new remainder when you divide 12 into 66 is 6. In the next step, a becomes 12 and b becomes 6. The new remainder when you divide 6 into 12 is 0. In the final step, a becomes 6 and b becomes 0. At that point, the algorithm ends because b is 0. Amazingly, the value of a is 6, which is the GCD of 78 and 66. Why does this work? The key step in the algorithm is where it sets a equal to b and b equal to a mod b. That works because GCD of ab is the same as GCD of b and a mod b. So the question is, why is that true? Consider the definition of a mod b. If you use r to represent the remainder after division, then by definition of the modulus, you know that a equals m times b plus r for some integer m. Now suppose g is the GCD of a and b, and look at this equation. You know that g divides evenly into a because it's the divisor of a. It also divides evenly into b because it's the divisor of b. If g divides evenly into b, then it must also divide evenly into m times b. Now if g divides into the sum on the right of the equal sign, and it also divides evenly into one of the pieces of that sum, namely m times b, then it must also divide evenly into the other piece of the sum. That means it must divide evenly into the remainder r. That proves that the GCD g must also divide evenly into the remainder of r. Each time you switch the variables around, the GCD g is still in there. The only way g can fail to divide evenly into the remainder is when the remainder is 0. That's when the algorithm stops and the GCD is left in variable a. I won't show it because it's even more confusing, but you can prove that the size of a and b is cut at least in half every 2 trips through the algorithm's while loop. Because the algorithm periodically cuts the size of the problem in half, it has order log n performance. That means it's a very fast algorithm even for large numbers. It could take you years to factor two 50-digit numbers to find their GCD, but you can find the GCD almost instantly with Euclid's algorithm. In another lesson, I'll explain how you can use the GCD to calculate the least common multiple of two numbers. You may want to try implementing Euclid's algorithm in your favorite programming language. Try finding the GCD of some really big numbers and see how fast the algorithm is. In this lesson, I'm going to explain how you can calculate the least common multiple, or LCM, of two integers. The LCM of two integers is the smallest value that is a multiple of them both. For example, 60 is the least common multiple of 12 and 15 because it is the smallest integer that both 12 and 15 divide into evenly. Note that this isn't the same as the product of 12 times 15, which is 180. If the two numbers share any common factors, then their least common multiple is smaller than their product. One way to find a least common multiple is to find the prime factors of the two numbers. Then use each factor enough times for both of the numbers in the least common multiple. For example, let's calculate the least common multiple of 12 and 15. 12's prime factorization is 2 times 2 times 3. 15's prime factorization is 3 times 5. Now we look through the prime factors and include as many as are needed for both numbers. 12's factorization includes two 2's, and 15's factorization doesn't include any, so the least common multiple should include two 2's. Both 12 and 15 include one 3, so the least common multiple must include a factor of 3. Finally, 15 includes a 5, so the least common multiple must include a 5. That means the final least common multiple is 2 times 2 times 3 times 5, which is 60. This method works, but factoring large numbers can be very difficult, so this method won't work for large numbers. A better approach is to use the greatest common divisor. It turns out that the least common multiple of two numbers is their product divided by their greatest common divisor. For example, the least common multiple of 12 and 15 is their product, which is 180, divided by their GCD, which is 3. 180 divided by 3 is 60, which is what we calculated earlier for the LCM. That's all there is to the LCM algorithm. Calculate the GCD using Euclid's algorithm, which is described in another lesson. Then divide that into the product of the two numbers. Euclid's algorithm has an order and runtime, so the LCM algorithm does also. I want to say one more thing about this algorithm. If you're working with big numbers, the product of those numbers might be too large to easily store in the computer. For example, suppose you're using 32-bit integers and you want to find the LCM of 10,000 and 20,000. Their LCM is obviously 20,000 because 20,000 is a multiple of 10,000 and also of itself. Unfortunately, their product is 200 million, which is too big to fit in a 32-bit integer, so the program would crash during the calculation. You can still perform the calculation, however. You just need to perform the division before the multiplication. Because the GCD divides evenly into either of the numbers, you can divide it into one of them before you perform the multiplication and you won't suffer from rounding errors. For this example, if you divide 10,000 by the GCD 10,000, you get 1. Then when you multiply 1 by 20,000, you get 20,000 as you should. More generally, for any pair of numbers a and b, you can start by dividing a by the GCD of a and b. Then when you multiply by b, the result isn't as large. It may still be too big to fit in a small integer or whatever data type you're using, if the least common multiple is really large. But at least you won't be stopped unnecessarily by a large intermediate value. The working files for this lesson include the file gcd.zip, which contains a C# example that calculates greatest common divisors and least common multiples. You might want to try to implement the least common multiple algorithm in your programming language.